In this video, we will try to understand the attention mechanism in graph neural networks. So the paper that we'll be trying to discuss is Velikovic 2018 GATT paper, which is Graph Attention Network. So as you know that in a graphical model, you have nodes, and those nodes can be treated as samples, or you can represent samples as nodes. And each of these sample or node can be represented by a raw feature vector. So we say, okay, that's the raw feature vector we have H naught. Now, this raw feature representation that may be a bag of words or some raw representation may not be quite ready or optimal for classification or clustering. And that's why we want to update this feature vector representation in a way that becomes friendly in terms of clustering and classification. So one of the goals here is to update the feature representation iteratively by injecting some attention information in the feature representation. And by updating through neural network, we may be willing to come up with a compressed representation of a feature. So let's say if this was a d-dimensional feature, we want to obtain a rather compressed representation of this embedding, which is m-dimensional, which is much lesser than d. And that m-dimensional feature representation should not only be good for classifying these samples or classifying these nodes whatsoever, but also it will also inject or infuse the relationships between or the attentions paid between these nodes and samples as well. So the idea here is we want to have some sort of embedding where the samples or the nodes that are of similar type or that belong to the same cluster should be learned together or should be paid more attention versus the samples that are dissimilar. So if I have this H naught representation or embedding representation for sample one or node one, then this representation should be updated by taking consideration into the embedding of similar nodes. So if I have similar other nodes with other embedding representations, so I need to have some sort of weighted representation of this one, weighted representation of this one to be able to update my feature representation or embedding for that. So in that way, I'm paying attention to my nearest neighbors to be able to refine my feature or embedding representation. So let's try to formulate this thing in a formal way. So like I said, we have a raw feature representation. And one of the things I can do is I can input this into my graph layer, neural network, graph neural network. So this is what we call layer one, or I'm representing as an L1. So inside L1, a lot of things will be happening. And then what you get is H1, right? And inside my approaches will be more top-down approach. So I'm starting from the top architecture, then I will dive down. And then I have H2, and in that way, the final representation, let's say, coming after the layer 6. So inside this layer, what you have is you have multiple heads. So multiple heads and is basically parallel representation of your feature or of your neural network architecture. So essentially what you have here is, so I'm trying to zoom in into this black box. So what you have is this H gets into an MLP, which is a neural multi-layer perceptron neural network where you have trainable weights and biases. And once you project that, so essentially what you do here is you get some sort of projection of this one. And what I mean by that is if you have if you have m number of d-dimensional features, which is represented by n number of these samples, so this weight matrix needs to be m by d. So in that way, what you get is a representation which is m by n. So you have n of those nodes, right? So now the first thing we have to figure out that out of these n nodes, you can consider a pair of nodes. So if you consider those good old adjacency matrix, then you can obtain this pair of nodes. And the first thing we have to do is we have to calculate the self-attention. And the way we calculate the self-attention is using this following formula, EIJ. That means how much attention node I is paying to node J, how much attention. So that's something we will be calculating. Here, A is basically a trainable matrix, weight matrix. We're going to be talking about that in a bit. So the first thing you have to do is you take W times this HI, so whatever the hidden representation for ith node, or whatever the feature representation you have for the ith node, right? So instead of putting this 0, I should have put this 0 over here, over here, just to avoid the confusion. This is over here and over here. So that's the ith node. So we just concatenate the response from the ith node and concatenate the response from the jth node, right? So once you do that, you get something like this. Now you need to understand that the dimension of this one would be d by 1, and the dimension of this one would be m by d. So in a sense, if you concatenate these two things, the dimension of this whole thing would be 2m by 1, right? So if you do matrix multiplication of this one, this is going to be m by 1. This is going to be m by 1. If you concatenate these two vectors, that's going to be 2m by 1. And the dimension of this one would be, the dimension of A is going to be 1 times 2m. And if you take a transpose of this one, you get it's going to be 2m times 1. If you take a transpose of this one, you have 1 times 2m. So in a sense, your EIJ will be just a scalar value telling me what is the attention score for ith node to jth node. And that's going to be just a 1 by 1 scalar value. So as you can imagine, that this E can be represented by a kind of a symmetric matrix where the matrix is n by 1 if you have n nodes in your graph, right? So once you have this self-attention, the next thing we have to do is we have to normalize this. So the way we will be normalizing these things, that we will be updating this EIJ by just using a leaky ReLU function. Good old leaky ReLU. Those who are coming from neural networks should be familiar with this by now. So once you project this to the leaky ReLU function, you get EIJ. And the next thing is you have to obtain the normalized attention score. So in a normalized attention score, you have alpha ij, which will have the exponential function of EIJ divided by sum across. Now, this is something important. What we're trying to get to is we're not going to take the sum across all other nodes. We'll be focusing on the nodes that are within the neighborhood of the ith node. So by Ni, I means the set of nodes that are in the neighborhood of the ith node, right? So I'm trying to be kind of a selective. So, and then this is K, right? So this is going to be IK, right? So this is what we're trying to get to because we'll be normalizing by the nodes that are in the neighborhood, but not by all. So in that way, we get a more normalized version, because as you know that this is a softmax function. And the beautiful thing about softmax function is the sum of all values for a given node. So if we take a sum across I with all nodes, alpha ij, that should be, this value should be equal to 1. So what I mean by that, that alpha 1 1 plus alpha 1 2 dot 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 alpha 1 whatever. So if you take the sum, it's going to be normalized to 1. So this is how we will be normalizing. So now we have this alpha ij. So in a sense, what we did is we started with eij, which was our good old eij matrix. And we transform this thing to our alpha matrix, which is alpha ij. And this is a symmetric matrix. Now, the question is whether this will be symmetric or not. Now, it may depend on the fact that the neighborhood that you will have for I node may not be the same neighborhood you will get for the J node. So for different I node, the neighborhood may change. And because of that, this matrix may not be symmetric. So that is something to keep in mind. So now we have our attention score. Now we will be using this attention score to do quite a few things. So let's go back to this black box. What's happening inside this layer black box, in the first layer black box? So we have this H naught, and this is our MLP. This is our layer 1. And so the way it's going to happen is you need to have the updated. So I shouldn't put 0 here. I should be putting 0 here. You should be getting some updated H from this one to this one by doing the following: is you have to concatenate. So before we concatenate, we have to take the sum across, because you need to understand that this is for the ith node, and this is the ith representation updated after the first layer. So, and simply because this is ith node, so we need to get the sum across all the j's, for example, right? So this j will be from the neighborhood, whatever neighborhood we have for this I node. And then we have our good old alpha ij. And then we need to have the response that is coming out of this MLP, which will be, like I mentioned before, W H J. So remember, this is a vector. These are all vectors. And then what we would like to take is the sigmoid on top of that. Okay, so what's happening here? The thing that's happening here is, I'm going to write it in a very simple way, that I want to understand how this embedding for node I should be formed by taking the embedding, linear combination of the embedding of its neighborhood embeddings. So in other words, if I have, let's say, 3 different neighborhoods, so for example, H1 is one neighborhood, it is one node, and its neighborhood, in its neighborhood, it has H2, H2, H3, and let's say H4. So what's going to happen here is I need to consider H1. Let's assume that in this particular case, I equals 1, right? I equals 1. So if you expand this summation, what I'm going to get is alpha 1 1 W H1, right? Because I'm considering 1 within the neighborhood of 1. That means node I is also belongs to the neighborhood of node I, right? Plus alpha 1, 2, WH2, alpha 1, 3, WH3, alpha 1, 4, WH4. So as you can see here, I'm trying to update the embedding for the ith node or ith sample by taking a weighted sum of the embedding from itself and also from its neighborhood, right? And this weight basically tells me whether or not this embedding for I should pay more attention to the embedding of node 3 in this particular case, because possibly node 3 shares more information with node 1. So in that way, I'm taking the relationships between the nodes within the embedding to be able to refine my weights. So on top of that, what we need to do here is inside this black box, we have multiple parallel branches. These are called heads. So in other words, this MLP will be executed in K independent branches that we call heads. That means for head equals 1, we will have one set of W's and one alpha. And for head equals 2, we will have another set of alpha and W's and so on and so forth. So these are just parallel MLP branches within a graph layer. So after this one, what we want to do is we want to concatenate these responses for K equals K number of heads within a given layer. So in a sense, after doing all these things, as you know, the output response of this one would be what? Once we apply this whole thing, let's assume that this is a kind of a scalar value. This is another value. So after taking the sum, we're going to get a scalar value. But at the end of the day, what we're getting here is actually, well, because this is alpha is a scalar value. This is m by d, and this is d. This is 1 by d. So d by 1. So essentially, what you have is a sum of these vectors, which are all m-dimensional. So you have an m-dimensional representation here. And if you concatenate this m-dimensional embedding for k of these heads, this concatenation is going to give you k times m-dimensional vector. That's what you're going to get. That's what you're going to get after the first graph layer. So I'm saying L1, because inside this graph layer, you have k of these heads, right? So here, after concatenation, you're going to get an embedding which is mk dimensional. So what you do here is you fit this embedding. So let's say this is 0. This is the response after the first it's not a hidden layer, it's a graph layer. And then you feed into the second graph layer. And in the second graph layer, as before, you have multiple of these heads, right? And once you input this one, you get the second representation of that embedding, right? So what we're trying to do here, we're sequentially refining this raw feature vector into better representation of this embedding through multiple heads and multiple serial layers. So here we had k heads, here we had k heads, and as well as this will be mk dimension, right? So what we do is finally, when we reach to our last graph layer, what we do is instead of taking a concatenation in the first layer, that means in the last layer, we're going to have k of these heads. So instead of concatenating the k of heads, we're going to be averaging. And the way we're going to be averaging is our final representation at the final layer, where L equals L, will be represented by 1 over K, because now we will be taking the average across K heads in this final layer. So for that reason, we have to take the sum and average. So last time we used concatenation symbol, remember here? Instead of using concatenation symbol, we're going to be averaging across K heads, and the rest of the expressions will remain the same, because you have to take the weighted sum of the embedding as before, and K stands for K different heads. And this is ij. We explained this thing, but now instead of concatenating, in the very last layer, we'll be averaging. And if you take the average, because now you're dividing by K, this whole thing was M by K. If you divide it by K, the dimension of the very last embedding will be M dimension, right? Now you take this M dimensional feature vector, which is for the last layer, for classification. If you want to do a binary classification, or if you want to do clustering whatsoever. So there are two things to remember, that each graph layer, you will have multiple of these parallel heads, and each of these head is an independent MLP that has its own alpha attention module. It has its own weight matrices, right? And at the intermediate layers, we'll be concatenating the embedding across those heads so that we can retain maximum information. So as we sequentially feed forward towards the final head, after the final head, instead of concatenating, we'll be then averaging those MK dimensional head responses into M dimensional responses. So our final feature vector will be M dimension, and that is what we'll be using for classification. So if we put together like this way, so this is my raw response, this is my layer 1, and this is the response after layer 1, and this is the response after layer 2, dot, 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 dot. Let's say we have 6 of those layers, then this will be the layer 6, and the dimension of this one would be just M dimension. And then let's say for binary classification, we want to project it to one output node. And let's say we're doing a binary classification, right? So our loss function would be aiming to minimize this cost function, right? Because this is the classification loss we're trying to minimize. So when we try to, so after the first epoch, so epoch number 1, so when you do the first epoch, you just feed forward these things sequentially. And after the first epoch, you get this loss, and you use the loss to back propagate and update the weights, all the weights at the different heads that you have in this back propagation function, and so on and so forth. So what you do here is you just back propagate the weights. So if you keep training this thing, let's say for 100 epochs, what's going to happen is, the hope is not only it will try to improve the classification, but also it will try to get you some feature embedding or feature representation for your individual node or individual sample, such that inside it is infused or injected with the attention information, because each of this block diagram, as I kind of explained, is updating this H1 in the next layer by taking some sort of linear combination of, or attention weighted combination of the embedding of the neighborhoods. So in that way, the attention mechanism is kind of infused, and once you go and keep training this thing, you finally obtain your alpha matrix for each of these head and for also for the final layer, and you should be able to use this final edge not only for classification, but you can do clustering. And it will be interesting to see whether this clustering, through this clustering, whether the embedding of the similar nodes are kept closer, because we're injecting the attention between the sample embeddings under the assumption that those samples are within the similar neighborhood. So if they're not in the same neighborhood, we will not use that embedding information into our attention calculation. That means that particular node will not pay attention to a node that does not belong to its neighborhood.